네, 안녕하세요. 네, 지난해 11월부터 달려온 10talks 업스테이지 컨소시엄 세미나의 특별 세션 마지막 시간입니다. 네, 저희 세미나는 다시 보기와 강의 자료를 제공하고 있습니다. 지금 보고 계시는 유튜브 영상 설명란에 발표 자료 다운로드 페이지와 이전 회차를 포함한 전체 자료와 영상을 보실 수 있는 링크를 넣어두었으니 확인하시면 되겠습니다. 네, 본격적으로 시작하기 전에 안내사항이 하나 있는데요. 오늘 세미나는 연사자가 외국분이십니다. 네, 발표를 영어로 진행하기 때문에 한 가지 안내사항이 있습니다. 바로 크롬에 있는 자동 번역 기능인데요. 크롬 브라우저에서 자동 번역 기능 관련 내용을 영상 아래에 안내란에 기재해 두었습니다. 한국 분들은 한국어로 된 안내만 읽어주시면 됩니다. 설정하시는데 2분 정도면 충분하니까 지금 바로 시도해 보시기를 권장합니다. 만약에 사파리 등 다른 브라우저로 접속을 하셨다면 크롬으로 다시 접속하셔서 수강해 주시면 감사하겠습니다. 네, 신청하신 이메일에도 같은 정보를 기재하고 있는데요. 일단은 지금 바로 필요한 정보들은 바로 영상 하단에 기재하고 있으니까 바로 확인해 주시면 되겠습니다. 세미나 이후에 추가로 정보 확인이 필요하시면 이메일을 확인해 주시기 바랍니다. 네, 그리고 오늘도 세미나 후반부에는 Q&A가 있습니다. 네, 오늘 주제와 관련해서 궁금한 부분들은 질문하셔서 얻어가시기를 바랍니다. 영어로 질문이 가능하신 분들은 영어로 기재해 주셔도 되고요. 한국어로 기재해 주셔도 제가 번역해서 전달 드릴 예정입니다. 네, 편한 방법으로 Q&A 남겨주시면 되겠습니다. 네, 본격적으로 오늘 세미나 시작해 보도록 하겠습니다. 오늘 세미나는 비디오 모델에 관한 내용입니다. 연사자인 사약 폴은 버깅페이스에서 엔지니어로 근무하고 있습니다. 네, 오늘 여러 사례들과 함께 실무적인 이야기들 많이 준비하셨다고 하니까 기대되는 마음으로 모셔보도록 하겠습니다. 네. Hi, Sayak.
Hey, hi.
Please begin your presentation.
Right, cool. Hi, everyone. My name is Sayak. I'm really pleased to be here today, even in an online capacity. I wanted to talk to you about the state of video generation models, that too particularly open video generation models, because as I understand it, many of us are quite big proponents of open models. So I wanted to give you a primer on the current state of open video generation models and also where we are headed. I want to start by acknowledging that even though I am from India, I am currently giving this talk from India, it doesn't feel like I am giving this talk to a foreign country, because I have collaborated with a lot of friends from Korea in the past few years, and I wanted to show you some examples of those collaborations, of those wonderful collaborations I have had with many universities from Korea. So you might be able to find some names that you might recognize, but yeah, these are some of the collaborations I have really loved engaging myself in, and I'll cherish them for the rest of my life. So yeah, so I feel like I'm not unknown at all. I have been in the Korean AI community for a while. So yeah. Okay, enough of that talk. This is roughly what I wanted to talk to you about. I'll give you a brief overview of some of the most popular open video generation models. Then we will discuss their existing capabilities. Then we will also talk a bit about how we can extend their capabilities. Then I want to spend some time on their limitations and what we can do about them. And hopefully by the end of this talk, there will be enough time for us to do some Q&A session. Yeah, I think you can reserve your questions till the end of this talk. I'm sure there will be enough time for that after the talk. Okay, let's get started discussing the introductions, the trends in the open video generation models. I'm sure we probably all have seen this video. I'm gonna switch to full screen because when the OpenAI Sora model had come up, this video got really popular, and it has that realistic look to it. And also on the right hand side, I have also provided the prompt that generated this video. By the way, this video is entirely generated by a model called Sora, which is from OpenAI. And the prompt that generated this video is on the right hand side. And I also have to say that the prompt is really long, and even for me as a human being, the prompt is quite complicated to parse in the first place. But that's the thing, right? That's the thing with models, video generation models like Sora. They can somehow parse all the concepts associated with that prompt, and they can somehow meaningfully represent them and also generate spatiotemporally video frames out of them. And I must say, this is quite a feat. Like, as I was mentioning, as a human being myself, it would be pretty hard to think about how would I go about generating a video, let alone an image, a video from this long prompt. But models like Sora can do that for us. So I just wanted to give you a pretext of what we have been able to achieve so far, because I think this video established a benchmark moment in the area of artificial video generation. And then, since this talk is about open video generation models, I wanted to share the names of some popular open video generation models. LTX is very popular. 2.2 is also very popular, and then Hunyan is also very popular. Throughout the rest of this presentation, you will see a lot of cute animals. So yeah, just embrace yourself for that. I feel very sorry for the poor cat in the middle, but I hope you can also realize the fidelity and the depth of the video examples that I have shown in this slide. Also, while we are at it, it's important to take a note of the different models that we will discuss throughout the rest of this talk. They come in all shapes and sizes. For example, the most popular model 1.2.2, it comes with an Apache license, but it also has a very high memory consumption requirement. Like, it takes almost 65 GBs of accelerator memory, but it's also very popular. It has a very good community ecosystem around it. Then there are other, smaller models like LTX and Mochi that do not take as much, but they have restrictive licensing in some of the cases. The quality may not be on par with 1.2.2. So all in all, 1.2.2 is a really good video generation model. It's an open video generation model for the community to play around with. And I have also mentioned the checkpoints, the checkpoints that you can check out on the Hugging Face Hub platform in case you cannot wait to get started. And you may have also heard about these models, such as VO from Google, Sora, as we discussed, Runway, Pika, Kling. But these are all closed video generation models, and we are not going to be talking about them in this talk. Also, just an important note, or let's say it's a minor note, doesn't really matter for this talk. But the models that we will be discussing in this talk, they are majorly based on this concept of diffusion and flow matching. Other families of video generation models exist, but those are not covered in this talk. All the models that we will discuss from this point on, they are based on either diffusion or flow matching. This is a concept in AI. It's okay if you do not know about it, but I just wanted to call this bit out. While we are at it, I thought it also might be a good idea to give a brief introduction to how diffusion models work. Well, a deeper introduction would have taken a separate lecture, but I really want to keep it brief in the interest of time. So the idea of diffusion model is the following. What happens when we try to refine a noise vector so that it becomes a realistic data distribution? In this case, that realistic data distribution is the distribution of natural images. So what happens when we try to start from a random noise and we try to denoise it over a few iterations such that it becomes a realistic image? So diffusion in many ways works like that. And also, it's not a one-shot process, it's an iterative process. You start from a random noise drawn from a Gaussian distribution, and then over a period of time, you slowly denoise it unless you have an expected realistic image, such as the cute cat we see in this slide. And when we try to condition this denoising process with, say, text, for example, a photo of a white fur monster standing in a purple room, you get images like this. I'm sure we all can agree that in reality, these creatures cannot really exist, but somehow, today's modern image generation models can get very creative, especially if we prompt them with creative inputs. So yeah, that's like text to image generation models, but in an extremely brief context. Now, this talk is about video generation models. Can we extend that concept similarly to text to video generation as well? So for example, if we wanted to go from this text prompt, a cat looking like a tiger, all the way to the right hand side to like a series of frames depicting a video, what we would need to do. So in this slide, I want to give you a visual representation of how different components are connected in a diffusion model, and hopefully that will make things even clearer. So we have our textual input, a cat looking like a tiger. We have to find a way to embed that textual input. So it goes through a text encoder. We can also use multiple text encoders, but that detail does not matter for this slide. So we find a way to embed the input textual prompt. We have the embedded text representation. We have that, and then we just saw that we start from a randomly drawn noise, and then we iterate it over a period of time conditioned on, let's say, some text inputs. So we also have some noise that we have drawn from the Gaussian distribution. And we also have a time step, a notion of time step that tells us where in that denoising trajectory we are in. And all of that goes into a diffusion unit or a diffusion transformer architecture, which we also call the diffusion backbone. And this is really the heart of everything that we have been discussing. So these three inputs go into the diffusion backbone. It's invoked over a period of time. We get our refined latents or whatever we get from the random noise, and we denoise it. So let's say we have our refined noise over after running the diffusion backbone for a couple of times, and then we pass those refined latents into a decoder, which gives us the actual pixels of the frames that we want. So this decoder gives us the sequence of the frames, which we can serialize as a video. Now, one important detail to call out here is this whole figure depicts a latent space diffusion model. As we can see, we are not directly outputting the pixel values of the frames first. We are first outputting the refined latents, and then that goes into a decoder, which gives us the pixels back. We could have generated the video pixels directly. That would have been a pixel space diffusion model. But latent space diffusion models are far more popular, and they take far less memory. So and latent space diffusion models are like way more popular than pixel space, almost to a point that we do not have to worry about pixel space diffusion models at all. So yeah, so that's roughly how different components within a diffusion pipeline, they're connected. And another important detail to call out here is diffusion is not about a single model. As we can see, there are different components, even model level components involved in a diffusion pipeline, such as a text encoder, a diffusion backbone, and a separate decoder. So diffusion is not about just a single model. So that's also an important detail to keep in mind. And we just discussed what are the main components for text to video generation, but the capabilities of current video generation models, they extend well beyond just text to video. Some of my favorites include image to video, multiple reference images to video, frame interpolation, video to video, post to video, and so on. And let's see some of these examples in action now. So since we will be talking about use cases from this point forward, I also wanted to introduce the library that I work at, that I get to work on at Hugging Face. It's called Diffusers. So it's like an open source Python library that where we want to give you access to the state-of-the-art open diffusion models and flow models for image, video, and audio generation. It's not just about image. We cover 3 different modalities. And we try to do that in a really accessible manner. But yeah, that's about diffusers. Now, since we are talking about video generation, I wanted to give you a heads up into what it looks like to code with diffusers to go from a simple text prompt all the way to a video. So this is all that it takes, given you have access to a GPU, if that's the case, this is all that it takes to go from a text prompt all the way to a video. So the code snippet has a bunch of imports. Then we are defining what model we want to use. Here I am using the 2.1 model, not the 2.2. And then I'm loading the model, I'm placing it on my GPU, and then I'm defining a prompt, and then I'm basically calling the model to generate the video, and then I'm exporting it. If you have used the transformers library from Hugging Face, all of these, the look and feel of the methods could feel quite familiar. And diffusers does not differ a lot from transformers in terms of philosophy and so on, but it is a different library. So yeah. But with that, I also want to give you a heads up about the memory consumption of this script. Without any kind of optimization, it takes about 48 GBs to run, which is a lot. 48 GBs to run just to generate a video is a lot. And not every one of us, has access to GPUs with this kind of memory. So yeah, what do we do about it? As I was mentioning, we try to make things accessible within diffusers, and we try to do so by providing various offloading strategies that have different trade-offs. We also provide easy support for quantization, and there are multiple quantization backends within the library. We also provide support for memory efficient attention techniques, and we have a bunch of guides that might be useful for our users who have access to only consumer GPUs. So check those out if you're interested. Now, with all of the accessibility recipes that we provide within the library, I was able to combine quantization and offloading, and I was able to reduce that memory consumption down from 48 gigs all the way to 11 gigs. So that's a significant number. 48 gigs to 11 gigs. That's a significant reduction. And I was able to do so by combining quantization with model offloading. So applying quantization is also easy. Here I am using bits and bytes, NF4, the quantization type that is, and I am using a form of offloading called group offloading, which basically overlaps data transfer that you need during the offload, and that offloading is overlapped with actual computation. So let's say when you are performing computation with a layer, the parameters of the next layer that will be needed for the next part of computation will start getting fetched in a separate CUDA stream. So that's how we are able to overlap data transfer with actual compute. So you do not incur a whole lot of overhead from typical offloading techniques that you may have seen. So we support all of that within diffusers. And yeah, I mean, we are applying quantization. That means we are also getting a bit of quality loss because we have access to limited number of bits that we can use to represent information. So quality also takes a hit if we are not careful enough. It's important that we experiment with different quantization recipes, like which layers we should exclude from quantization, which layers we should include in the quantization process. All of these are pretty important things to experiment with, and I highly encourage you to experiment with these things before pushing something to production. So in this example, on the left-hand side, I have the non-quantized variant, and on the right-hand side, I have the quantized variant. Like in terms of the depth and the fidelity of the video, we can see it's pretty much unaffected from quantization, but the cat is doing something crazy when the model is quantized. So yeah. As I was mentioning, we have use cases that go well beyond just text to video generation, and I would like to discuss them now. So let's start with image to video. I think this is perhaps one of the most practically relevant use cases. So the idea is we have a starting image, this cute cat, and we also have a text description of what we want to see in the generated video. And yeah, not bad. The video starts from the input condition, and we are able to successfully generate something that mimics the input text description. Isn't that cool? So yeah. And then we have got a starting image, and then we have got some text description, and we can go all the way to a video that also has some audio. This does not have any audio, but the example that I'm about to show you will have audio, giving us a true sense of a video. A video is supposed to have some audio, right? So this is our starting image, a baby astronaut. And then I have a text description, which is again very long and very creative and very imaginative. This starting image itself is very creative. I would like to say a baby astronaut hatching out of an egg, that too on the surface of the moon. So, and this is the video. Note that it also has audio. Pretty cool, isn't it? Yeah. And then maybe we have a starting image, and we also, let's say, have some starting audio that we want to see in the generated video, which is again very cool, right? And we of course have some text description. So what do we do? So yeah, in this case we started with the same starting image. Let me also play you the audio. This is the audio. This goes as input to the video generation model. This is the text description, which is not imaginative. It's a simple text description, and this is the starting image here. So yeah, and this is the video that we got. Cool. Now you might have multiple different images, and you are looking to find a way to use those reference images in the video. And in this example, I have a cute robot, I have a GPU poor hat, and then I have a sunglass, and I want my video generation model to use all of these reference images and get me a reasonable clip. And I also want this robot to dance across the beach. And as we can see, the model was able to successfully place the sunglass on the robot. It was also able to successfully place the hat on the robot, and it was also able to successfully make it dance, which is pretty cool. Yeah. And there are all like there's no shortage of creative use cases in the video generation space. In this case, I have a starting image where I have masked some portions of this cute penguin, and I have also provided some basic text description, and I want the video generation model to use this starting image, fill the masked region, and then get me a video, which is quite a task even for me as a human being. So yeah, there we go. It's able to follow the text prompt. It successfully generates a tutus cart. It's able to successfully put it on the penguin and then create a mini video clip from it, which is again very, very cool. Frame interpolation is we have a first frame, we have a last frame, and then we want the video generation model to fill in the intermediate frames. Of course, we can condition that process with a text description of what we want to see in the intermediate frames. So yeah, let's go. Not bad. Yeah. And then this is particularly very prevalent in robotic arm controls and applications like those. Maybe we want the video generation process to start with some structural guidance. In this case, we are using canny filter and a trajectory of where I want the subject to move around, and I was able to use this structural guidance to generate a cool clip where the cute dog is following a particular object trajectory. So it's also pretty cool. I'm able to spin his head around. And video generation models can actually be used for generating images as well, since video models learn like very rich information about the world, about how objects move and interact with each other, and so on. Those priors can be used to generate images as well. Like I have this again a very long text description, and I want a video generation model to generate an image out of it. So yeah, it's all possible. It's a static image, it's not a video. And it's the whole idea of using information from videos and video generation model to improve the field of image generation. It's becoming more and more common and prevalent these days, and this is actually one of the works that I did with some of my collaborators, where we wanted to improve the state of image editing that is grounded with physical awareness. So we were able to leverage the rich dynamics that videos capture of the real world to improve the physical dynamics in image editing. So for example, if we take this figure as an example, we have an input image and we have an edit instruction. For example, remove water from the cup. And if we look closely, when we are removing water from the cup, other models like Chrono Edit, they are removing the entire cup. It's not just removing the water. But when we just remove the water from the cup, the rest of the elements should stay in the cup, right? I hope you get what I'm saying. And then in the middle example, that's by far my most favorite example. We are asking the model to remove the ladder from the image, and other models like chrono edit, it's removing everything that's hanging on that ladder. Like, I asked it to just remove the ladder and not the clothes with it. And when we try to bake in the dynamics from the videos while training image editing models, these kinds of things get baked in the model. And as a result of that, we can see our model is able to successfully remove just the ladder and not the clothes with it. I hope this gives you a flavor into how video models are becoming increasingly more and more important for other domains such as image editing as well. I wanted to talk to you briefly about this another library called Fine Trainers, which lets you fine tune existing open video generation models on new data sets. And at Hugging Face, we did fine tune a couple of models to teach them new video effects such as dissolve, cakeify, and so on. And if you are interested to train on your favorite effect or maybe some other video clips, I highly encourage you to check out the Fine Trainers library. It's pretty fun. I have some concluding thoughts where I wanted to spend some time discussing the limitations of current video models. So yeah, a bit old, but all of the information that I have shared so far are within this blog post, State of Open Video Generation Models and Diffusers. So if you are interested to follow along even more, I can recommend this blog post. Yeah, like the most obvious question to ask at this point in time would be, where do these open models stand? Yeah, not very far actually. Like the first rows of this table, the runway model, the cling model, these are closed models, and on the bottom row, Skyreels V2, it's an open model, and we can see it's actually better than some of the closed models in some aspects, which is pretty cool. And we of course have some catching up to do, like in terms of video fidelity. The closed models are still better in terms of preserving object accuracy throughout the frames. The closed models are still better. So yeah, that sort of gives you a peek into what needs to be worked on, which is good, which gives us something, which leaves something on the table for us researchers to further work on. But we did come a long way, because this is from back in December 2023. This is from November 2023. And we can see that it's like the video fidelity is pretty poor. There's lots of static movements in the motion, like unwanted static movements in the motion. We can tell like this is generated. The realism aspect is missing. Whereas in some of the clips that we saw a couple slides back, those videos did feel real. Like it at least had that realism vibe, if I will. So yeah. But all in all, I would like to say last year the community did take giant steps in this area, and I would like to believe the 1.2.2 model did really start this revolution. But there were other significant works as well, but the fidelity and the depth of the videos that started really improving with the 1.2.2 model. Of course, there are limitations. Like I already gave you a hint of where the limitations stand prompt adherence is something you might run into often, like where the generated video is not following what you had described in the input text prompt. So I always recommend using detailed prompts, which is probably why we also saw a lot of detailed and imaginative prompts throughout the rest of this talk. Motion dynamics can be challenging. Like we can still see a lot of static movements in the generated video clips, but even today's video models can understand if motion is expressed in terms of cinematographic terms. And what I'm trying to say is, if we are clever enough to specify motion through cinematographic terms in our input text description, it could just work, because modern models can understand it. Some of the modern models can actually understand it. Video duration is a legit problem. Like, it's still very hard to generate a realistic video which has sufficient fidelity and depth that also goes beyond the 10 seconds horizon. So video duration is definitely an ongoing area of research, but significant improvements have also happened in that area. And I would like to suggest reading this paper called Skyrails V2, because it provides a very good example of how some of these problems can be approached in a multi-stage manner. And with that, we have come to the end of this talk. And I have already shared the presentation with the organizers, but if you wanted to just scan the QR or note down the slides link, I'll just keep the slide open for a bit. But yeah, I think we can start the question answers, because the talk is now done. So yeah, I would love to take questions and answers.
Okay, thank you. We will listen many questions from the audience. Sayak, could you please answer them starting from the top?
The first question is, the quality of video generation seems to be slightly subjective. How do you usually evaluate models? That's a good question, actually. So there's a metric for fidelity called VFID. Again, it's not a very reliable metric, but it's very similar to the FID metric that's commonly used in the image generation space. VFID is often considered as the proxy to measure fidelity. But then again, fidelity is not the only thing that we should be looking into to evaluate a video. There's like motion, then there's text to prompt adherence, there's object accuracy and all those other things. So I would suggest looking into the VBench benchmark for holistically evaluating video models. I hope that answers your question. There are a lot of copyright and adult image issues these days. How can we relieve those problems when creating videos? That's again a very good question. I think one, to get rid of the copyright issues, we could use permissively licensed models. For example, 1.2.2 is an Apache 2.0 model, so we can freely use it. So that, like, using permissively licensed models is a very good step to get rid of the copywriting issues. In order to prevent NSFW content, I think, like, even I am very hesitant to suggest, model-based filtering, because even model-based filtering can give you like false positives or even false negatives in many aspects. But I guess using that is a good step. Like you can use NSFW filters on a generated video or on a generated image, and then take it from there. Or you could, before showing the final results to your users, you could look into the confidence scores of those NSFW filters. If those scores seem a little uncertain, then you could flag it for human reviews. If they do not feel very uncertain, then maybe you could directly show the results to the users. But I think data level auditing and data level curation also goes a long way. So yeah, like both approaches. NSFW filtering, if you can't afford to do any safety fine tuning, or you can't afford to pre-train models from curated data sets. But if you can, do safety post training, or if you can afford to train models with a curated data set, I think those approaches of data curation can also go a long way. I found it interesting that using video data instead of images allows the model to learn transition priors. Are there any capabilities that a model could learn by training on video rather than images? That's also a very good question. I think it depends on what you want to do by training on videos rather than images. Like, for example, Chrono Edit is another good example where image editing was reformulated as a video generation problem. And in our work, physics edit, let me go to the slide. In our work, we trained on video data, and we did image editing itself. We did not cast the image editing problem as video generation. Instead, we trained for image editing with videos. I believe you could also learn, action dynamics. You could also learn activity recognition, all those classic things. But I think it also needs to correlate a bit with what you want to do by training on videos. So I think that's the important question to answer first. So yeah. How do you foresee image video generation technology changing the film industry in the future? Will we no longer need actors? That's again a very tricky question, I think. I'm already seeing like short, web series where the episodes are like entirely generated, but at the same time, like it's I am also seeing where many scenes are crafted with AI assistants. They are not fully generated with AI. I think in the long term, in order to make something truly significant, it will be AI assisted and not entirely AI generated. But the short content that we see, let's say 5 minutes of video clips each episode, I don't think those are like of high quality anyway. Those are short-lived, transient moments which I do not think fully capture the essence of an entire properly directed and properly shot film. So yeah, that's what I think. Video generation consumes a lot of GPU resources. What technology can we use to solve this problem so that fewer resources are used? A lot of things, actually. So that's why I want to shed some light into the memory consumption of some of the open video generation models and what technologies we could use. We could of course use quantization and model offloading. We could use memory efficient attention mechanisms. We could also use memory efficient kernels to do stuff. We could also use parser forms of attention. Many works such as fast video, they do exploit the sparsity properties of attention and leverage that very cleverly in order to reduce memory consumption. So yeah, all in all, I think these are some of the approaches that I would use at the post training level. But you could also think about architectural improvements even before you go about the post training techniques that I just discussed. Like for example, the LTX, the first version of the LTX model, it it started caring about efficiency at the architectural level itself, like operating on highly compressed latent spaces, operating with fewer number of parameters, and so on. So I think there's a bunch of approaches. You need to work out what works for you the best. I am a student interested in video generation research. If I were to pursue this field, what technologies would you advise me to focus on? That's very admirable that you are interested in video generation research. I think world models in general, they are kind of a very hot topic right now, and I think they will become more and more relevant in the coming years. So yeah, you could start looking into world models if you do not have a background on diffusion or flow matching. You could start learning about those things, and then you could take a look at some of the recent papers in video generation. Like you could have access to some of the papers I mentioned from my presentation. So I think that will be a very good starting point for you to gather enough inspiration and motivation. Yeah. Currently, the text generation model and the video generation model are separate. What kind of technology do you think will lead to their integration? Oh, I think you mean like unified multimodal models. If so, Meta actually released a really good paper yesterday. I think it's called, I forgot what it's called. Wait a moment. Native multi-model pre-training meta signing issue. Yeah, this is the one. I'm gonna mention this in the comments. Oh no, I'm gonna just send it to our organizer. Yeah, I just sent it in our private chat. If I'm not sure if it can be flashed or sent to the participants, but yeah, I think that paper talks at length about how we can unify multiple modalities that go well beyond just single modalities. So.
네, 지금 링크를 사약이 채팅창에 보내드렸습니다. 네, 다음 질문으로 넘어가겠습니다.
Beyond current text-based prompting, what are the emerging interfaces or technical trends that allow for more intuitive control over camera movements and angle, much like professional director? Technical trends. Okay, yeah. I think I already showed some of the examples, like where you can condition a video generation model on like trajectories and so on. You can also condition them on poses. You can condition them on starting images and so on. So I think those are pretty good interfaces to start off with. They also, like, the trajectory bit also provides you camera control over camera movements and angles, like different shot angles and so on. And short angles can actually be also specified in the prompt themselves. So yeah, I think those are exciting areas to start with. There are predictions that fake videos will cause many social problems in the future. How can we solve this problem? I don't think there's any definitive answer to this. I think social awareness is definitely a good first step. I'm no expert, but this is just my observation. Second is watermarking any AI generated content, be it visibly or be it within the metadata. That's also a very good step towards this problem. When converting images containing Korean characters into videos, the text often breaks up. To ensure stability, is it recommended to primarily use images of objects or landscapes without text? Yeah, I think that's a good observation. Personally, I am not a native English speaker. I am also not English. I am a Bengali, if my Indian descent is considered. Even like, I don't think like models generalize very well to like non-native languages. At least the open video generation model, some of the models do generalize to other languages like Chinese other than English, but I don't think they generalize well to like non-native text bits yet. So yeah, definitely using images of objects or landscapes is a better idea. Yeah. I have generated video with Heijen before, and I have confronted many issues related to poor understanding of specific language nuance and accents. In terms of voice issues in generating video, should the video generation model be developed or voice? I think it was translated because the last bit of the question I do not get, but I'll try to use my best judgment to answer the question. If you are asking about why it didn't follow particular instructions in the native language, I think the model simply wasn't trained well enough with the language that you confronted with. So it may have had its nuances. Regarding voice, I'm not sure which model. Heijen, I haven't personally tried Heijen, so I won't be able to comment more on the voice issues. But just know that it's quite difficult to, generate complex videos with complex audio embedded into it, because that's a pretty hard problem, and we are just starting. It's not like a very developed area, so the timeline might not be there yet for extremely matured and complex video plus audio content. So, but yeah, I know, like, this is a very impartial, like, very unfulfilling answer, but I wish I had more information, but sadly I don't.
네, 알겠습니다. 그러면은 네, 오늘 세미나는 이쯤에서 마치도록 하겠습니다. We really appreciate your time and effort today, Sayak. Thank you very much.
Thank you. Bye.
오늘 세미나는 여기서 마치는데요. 이제 저희가 연내에 추가 세미나를 기획을 하고 있습니다. 아직 공지가 제대로 나가지는 않았는데 필요하신 분들은 저희가 따로 한 번 더 공지 드릴 예정이니까 네, 한번 메일 확인해 주시면 감사하겠습니다. 지금 이번에 준비한 10talks 세미나는 특별 세션 3회차까지 해가지고 마치도록 하겠습니다. 네, 참석해 주신 여러분들 정말 감사드립니다. 다시 한번 인사드리겠습니다. 감사합니다.